Hello, everyone. This is Adam Gabriel, and today we will explore an advanced but very powerful technique we use with GPTs or LLMs. We can use those terms interchangeably. Um, what is a GPT? GPT stands for General Purpose Transformer. That means it is trained on uh, a lot of knowledge, so it knows a little about a lot. That's why it's GP, general purpose. Now, we can take a general purpose transformer and fine tune it with information in a specific domain to make it act in a more expert way in that domain. So in this case, we will take medical information and use it to fine tune LLaMa 2 from Meta so it becomes more capable in the medical arena. That is the concept of fine tuning, generally speaking. Take the general purpose transformer and fine tune it, add some information in a specific arena to make it more capable in that arena. We will be doing this on Google Colab, which is very useful when we're doing things of this nature because as opposed to having a big chunk of code that represents all our code all at once, let's say in environments like Visual Studio Code, we have our code broken up into smaller chunks. Sometimes a chunk is as small as just one line, and we can execute these chunks individually. Furthermore, we have these labels that are not executable, and they just tell us what's happening in each chunk below the label until we get to the next label. So what we're gonna do is execute the steps from 1 through 9a. So I'm gonna select all of those, and step 9a, which is where we will stop for now. Oops, okay, let's do this again. So I'm gonna select this and then shift select all the way till 9a. There we go. So I will be running all of this, okay, to start. So how do we do that? We go to the runtime menu and run the selection, and then unselect to see exactly what is happening step by step. So here it's loading installing the necessary libraries, and after it's done, you will see a check mark appear. Yeah, it did it, and it took 15 seconds. This one took just 2 seconds, and you can even see its progress along the chunk using this small black arrow here. So it's working its way down. Step 4 is done. Step 5, step 6, step 7. It's loading the data set. And then step 9, which is loading the pre-trained LLaMa 2 model. That's the one that will take the longest because the model obviously is a big model. So it occupies a lot of space, and what we're doing here is we're loading it to get it ready for the fine-tuning process. As we see, it is taking some time, but it will be over in a couple of minutes. Now, to give you a high level idea of what is happening here inside the model is that we're keeping the weights inside the model. The weights are where the information that was used to train the model is stored. We're keeping the original ones as is, which we also call freezing those weights, and we are creating an additional set of weights from the information that is used for fine-tuning. And once that additional set is created, then we're adding the frozen ones to the additional set to arrive at the fine-tuned weights. Another thing we could talk about is the fact that we're using a technique here called QLoRA, which stands for Quantized Low-Rank Adaptation. So how is this different from just LoRa, low-rank adaptation, and what advantages does it offer? So when we're doing low-rank adaptation, the additional weights, each additional weight is represented by 16 bits, meaning 2 bytes. When you're looking at a model with billions of parameters, billions of weights, so the smallest one from LLaMa 2 has 7 billion parameters, you're looking at gigabytes and gigabytes of memory. And it's not just any memory, it's video RAM, VRAM, which is the memory on the GPU, the graphics processing unit. And here we're using the most powerful one that Google Colab has to offer, which is the NVIDIA A100. And you can see that even for this most powerful one, the GPU RAM maxes out at 40 gigabits. So typically, if we do just straight LoRa, the video RAM we will need for fine-tuning exceeds what we have physically on the GPU. Now, if we quantize the process, and quantization simply means that we turn the continuous number that represents the new weights into a discrete number, we reduce the number of bits needed to represent the fine-tuned weight from 16 bits to 4 bits, meaning we divide by 4. And so, of course, this reduces our VRAM needs dramatically. And you will see when we get to the process of actual fine-tuning how this reflects in the GPU RAM usage over here. Now we're at 73% of the Model 1, and it says, as you can see, 1 of 2. So after it's done with the first half of the model, it will upload the second half of the model and do a quick check on itself to make sure that the model was uploaded successfully. There's nothing wrong with it, because then that would affect performance, and then we will be the model will be loaded and we would be ready to chat with it and see what the results are. Now, going forward or skipping ahead just a little bit, you can see that the very next step will be chatting with the pre-trained model. That means that that's the model that came from Facebook, from Meta, and it has the information that Meta has pre-trained it with, generally speaking, including medical information. So it will yield an answer, and once we're done with the fine-tuning, we will compare the answers from the model before it was fine-tuned, meaning the answer from the pre-trained model with the answer from the model after fine-tuning. Okay, the second half of the model, 2 of 2, is uploading now, and as soon as it's done, we will be ready to query the pre-trained model. Once again, you can see this is one of the most time-consuming steps in this procedure because the model is big. It's quite a few gigabytes, so reading it from Hugging Face, the site that houses it online, and putting it on the A100 GPU and the disk space surrounding it on Google Colab is taking quite a bit of time. But we're almost there. We're at the 70% mark now. Yep. So once we're done with that, it will do a quick self-check and we'll be ready to query the model and test it. All right, so now it's done with loading both halves and it's loading the checkpoints and it's going through them and everything is done and the process took 9 minutes. At this point, we are ready to chat with the pre-trained model. So we're gonna prompt it. The user prompt is, what is paracetamol poisoning? Okay, so we will run this step. So it's giving that information to the model and waiting for the model to respond. Now, in case you're wondering why didn't we get an almost instantaneous response like what we would normally with ChatGPT, for example, that is because we're using just one A100 GPU as opposed to nearly 20,000 on ChatGPT. So, of course, there is a significant difference in the response time. Okay, so we have our response here, and we will proceed with the rest of the procedure before comparing the responses. And before we do that, let's just point out, so inst and /inst are the ones that house the prompt. So this is the beginning of the instructions, the beginning of the instructions, the inst, and the end of the instruction, and what's inside the instruction, the exact user prompt that we gave it. What is paracetamol poisoning? Here, that's it. And then everything that comes after that is the answer of the model. Okay, so here until the very end of this line. Okay, now we're gonna execute the rest of the code which fine-tunes the model. So we're gonna select this cell and go all the way to step 14, shift select all of those, and you can see at this point we've used just less than 5 gigabytes of video RAM. Now observe what happens as we proceed with the fine-tuning. So again, we're gonna run the selection and then deselect so we can observe at a more granular level what is happening. So step 12 is done, 13 is done, and now we've started with step 14, and as you can observe here, the VRAM usage will start, or GPU RAM will start steadily increasing. Okay, it's asking me for my API key, so I'll get it. Paste it here, and the process will continue. If we look at the GPU usage, now it has climbed to 11.6. So to give you a little bit of explanation, what is happening here is that we're doing the matrix multiplication operations that are used to compute the new weights that we will add to the frozen weights. Matrix multiplication is done inside the GPU in the GPU RAM or VRAM, video RAM. So that is why we see it actually use a little over a quarter of all of the available RAM, VRAM. We are monitoring the process, checking in on it every 25 steps out of 100. So here we have a result at step 25, then step 50. The loss indicates how accurate our process is. So the lower the loss, the more accurate is our fine-tuning proceeding. So we start with a 1.7, then we go to a 0.84, so it is going in the right direction, which we also call converging, so there is convergence. I will tell you though that convergence rarely proceeds in a straight line. It kind of ping-pongs until it settles at the minimum value. So we see 1.7, then it goes to 1 to 0.8, and at the 7.5, instead of reducing from 0.8, it goes up a little to 1.3, not as high as 1.7, but it still went up, which is what I told you about the ping-ponging process. And then we will see what it settles at in the end, which is 0.7, which is indeed the lowest value that is present amongst all of these values. So it has settled at a minimum. Okay, at this juncture, we are ready to chat with the fine-tuned model. And so, of course, we use the exact same prompt and we execute this. Again, it does need some time to generate the answer because we're using one GPU as opposed to almost or around 20,000. Okay, so in the same fashion as before, what exists between beginning of instructions, end of instructions is the prompt that we gave it, and then after that is the actual answer. Now, none of us here, I'm assuming, none of the people watching are doctors. So to determine how the fine-tuning has actually improved performance, uh, I have two simple ways to do this. So the first, let's look at the pre-trained model, which is the model before fine-tuning, and count the number of symptoms for paracetamol poisoning that it gives us. 2, 4, 6, 8. Now, let's go to the model after fine-tuning and count the symptoms. 2, 4, 6, 8, 10. So right there, we can see that it has increased the quality, fine-tuning has increased the quality of the, and quantity actual, of the response, quantity in terms of the number of symptoms. It's obvious from that. Something a little more subtle, and I've already made this simpler. We don't have word wrap here. So I've taken the two answers and pasted them end to end in the notepad so we can take a look. So this is the answer. The first one is the answer of the pre-trained model, and the second one is the answer of the fine-tuned model. Okay, so what do I want to draw your attention to? Now, it starts the answer with a capital letter, which is proper English, but then when it separates paragraphs from each other, this one, the T is not capitalized. The I is not capitalized. The T again is not capitalized, while in the fine-tuned model, the S is capitalized, the T is capitalized, P capitalized, P capitalized. So again, the quality of the answer is higher because it's using proper formatting according to the English language in its response. Subtle, but showing what has happened. Finally, in case you're wondering why the answers are truncated, so in more severe cases, and then it stops, and then for the fine-tuned model, paracetamol, and it stops. That is because I have purposely limited the amount of output so that it doesn't take an unreasonable amount of time to generate the response, since once again, we're using just one GPU instead of a farm of GPUs. This has been an illustration of Quantized Low-Rank Adaptation, or QLoRA. I hope it has been illuminating. If you have any questions, please don't hesitate to get in touch with me. I hope you enjoyed this. Thank you.